We have already discussed the example of Euler path in our very first class on graph theory, where we were talking about how this subject emerged. We were discussing about this town of Prussia, where there were 4 components of land which were connected with 7 bridges, and people were looking at the answer whether they can take a walk through this island in such a way that they cover or they travel through each bridge exactly once. In this lecture, I'll give you two more similar situations, rather two more analogies for this so that we can easily understand our proofs and what we are trying to do. So when we were kids, we would do this, we would try to solve this puzzle. I think many of you might have done that. So we would ask our friend, okay, I'm going to give you a figure. What you have to do is you will have to draw that figure without lifting your pen or pencil. So you should not lift your pen and pencil from the paper, and also there should be no overlapping. The example which we would do was something like this. So you can actually try doing this. Can you draw this figure without lifting your pen from the paper and without creating any overlap? So let's say I start from here. I go like this. I'm stuck here now. So without lifting my pen, I cannot draw that other diagonal. If I try doing it in some other way, let's say I start from here and then I come here and I come here, I come here. Again, I am stuck. Without lifting my pen, I cannot draw that third edge. So this is essentially what we mean by Euler paths and Euler circuits. So whenever we are trying to do this, it actually means we are trying to go through each edge of this figure, right, in such a way that we traverse through each edge exactly once. So when I go here, when I come here at this end point, without lifting my pen, I cannot draw that edge. Why? Because in order to go there, I'll have to go through either this or this edge once again. Let's look at this figure here. So can we draw this figure without lifting our, can we draw this graph without lifting our pen from the paper? And it seems like for this figure it's pretty easy. So I'll start from this node 4 here. I'll go to node 3, then I go to node 0, then I can go to node 1, node 2, and then back to 0. Or I can start from 4, go to 3, go to 0, go to 2, 1, and then back to 0. So there is a way in this figure. So any graph which has such a path which I just showed you, so you start from one vertex and you go traverse all the edges of this graph exactly once. So no edge should be left out. So if I do something like this, so although I do not have an overlap, but I have not completed the entire picture. So it's not an Euler path. Similarly, we should not have any overlap. So whenever you can produce such a path, it's called an Euler path. And then we can make this problem a little bit more challenging. What we can say is we have to do the same thing. You start from one particular vertex and then you go and you try to reproduce this entire picture without lifting your pen, but you should end at that very place from where you started. That is the another version of this problem. And can you do that with this graph? So if I start from 4, I go to, starting from 4, we go to 3, we go to 0, 1, 2, and 0. And then there is no way to come back to 4. And then can you do it starting from some other vertex? Let's say you start from 0, you go to 1, 2, back to 0, and then 3, and then 4. But you started from 0, but you ended at 4. So you were unable to do it. So that is called an Euler trail. If you are able to do this, as an example, look at this figure here. If we try to do this, let's say I start from this node B here. I went to A, then I went to C, went to E, D, C, and then back to B. So I've again created this entire picture without lifting my pen, and I have ended at exactly the same place where I started from. So if a graph has such a trail, we call such a trail as an Eulerian trail. So that's the difference between an Euler path and an Euler trail. In trail, you should end at the same place, at the same vertex where you started from. In the case of path, that's not a necessary condition. So any graph which has this Euler trail, we call such a graph as Euler graph. So if you have at least one Euler trail in a graph, we call that graph as an Euler graph. So now the question is, here we have tried making this trail and we have ended in one, and then we state that yes, this graph is an Euler graph. Assume that again I give you a very big graph, let's say on 50,000 vertices. Can you tell me whether this graph is Eulerian or not? Do you have an Euler trail in this graph or not? And it might turn out to be very difficult. One way to do that is you figure out one such trail and you give it to me, and then you say that yes, since this graph has an Euler trail, it's an Euler graph. But how easy or difficult is that? Can we have some other properties in the graph with the help of which we can say that such a trail or such a path is possible? So do we have a litmus test? I've seen it in that video, but I'm giving a different. And now I'm going to give you another analogy for this Eulerian graph. So the first analogy we had was that of the bridges of Königsberg, I'm sorry. And then the second analogy we had was of this game where you draw that figure without lifting your pen. And the third analogy which I'm going to give you is a game. So what's a game here? Assume that you are living in a city, and this city again, like the bridges of Königsberg, in this city you have multiple islands, and these islands are connected with bridges. So I have these islands over here, and there are certain bridges between these islands. These bridges are nothing but the edges of your graph. And assume that a deadly disease is spreading in this town. What you want to do is assume that you are living here, and what you want to do is you want to break the connections between these islands so that the disease doesn't transmit from one island to another. So what you want to do is your house is in this particular island. What you want to do is you go to this island, and as soon as you go to this island you burn this bridge. So this bridge is now burnt, there is no more connection between these two islands. Then you start from this second island, you go to this third island over here, and as soon as you go to the third island, this bridge is burnt. So as soon as you use a bridge, the bridge is burnt. And then again you come here, and as soon as you come here, this bridge is burnt. So what your aim will be? Your aim will be to burn all the bridges, and after burning all the bridges, where you should end up? You should end up in your home island, not at some other island. So how do you do this? And if you'll think about it, if you are able to do this, it means that there is an Eulerian circuit in this graph. So you can go through every bridge, and once you are going through every bridge, it is getting burnt, and you burn all the bridges. So you can burn a bridge only once, because once you have burnt it, it doesn't exist. And after burning them, you should end in your home island. Here is a litmus test for an Eulerian graph. So we say that if a graph G has an Eulerian circuit, or if a graph G is Eulerian, this implies that all the vertices in the graph has an even degree. And how do we prove that? So we are going to prove it by contradiction. So what we are going to prove is the contrapositive of this statement. I hope you remember what contrapositive is. So what I'm going to show you is, if all the vertices in this graph doesn't have an even degree, which means that if there exists a vertex in this graph which has an odd degree, even one vertex which has an odd degree, this implies the graph is not Eulerian, right? And you can use this litmus test. So if you are given a graph on 100 million nodes, and you know that yes, there is a vertex in this graph which has an odd degree, you can actually say that the graph doesn't have an Eulerian trail. It seems quite it's not intuitive at all. How is it happening? So with the same example, let's try to prove it. So what we are saying is, what we have to prove it, if there is a vertex having odd degree in a graph, you do not have an Eulerian circuit in that graph. And with this same example of burning the bridges, we'll continue. So while you are setting out on your journey to burn these bridges, what you are doing is you are just moving from one island to another. So this is your home island. Let's name it H, from where you start. From here, you take a bridge and you go to some other island. Let's say island number 1. From there, you go to island number 2. From there, you go to island number 3. Sometimes you might be coming back from island number 3 to island number 1, and then again you might be going to some other island, let's say 4, from there to some other island 5. So you might be revisiting some islands. Maybe from 5 you go back to 2, and again from 2 you come back to 3, and from 3 you go to 6, so on and so forth. So you are going on this journey, and ultimately where you should end up, you should end up at your home island, and you should have covered all these edges. So what we are saying is, you cannot have an Eulerian trail if any of these islands over here have the number of bridges which is odd. So what will happen? Say in all these islands, there is an island which has an odd number of bridges. So ignore this home island for meanwhile. So assume that except this home island, for all other islands, if I have any island here which has an odd degree, so what will happen? So I'm actually using one of the bridges to actually come to this island. So with this bridge, I came to this island. So what happens if this island, let's say I say had just a degree of 1? Is it possible? So if any of the islands here have a degree 1, what will happen? So since it's not my home island, I use this edge to come to this island. And as soon as I come to this island, I have burnt that bridge. So this island is now left with no bridge. I'm trapped in this island. I cannot go out. And since I cannot go out, I can't reach my homeland. I do not have a Eulerian trail, which I was looking for. So it's not so possible that any island has a degree of 1. So if that's happening, this graph of islands will look something like this. So these are the islands connected with bridges, and there is just this one island which has a degree 1. So you start from your home island, you come here, and as soon as you come to this island, this bridge has been burnt, you can't go back, you are trapped. So degree 1 is not possible. So whenever you have degree 1, you should have one more bridge here to get out of this island. So you go out of this island. Similarly, can it have a degree 3? Again, what will happen if it had a degree 3? So you burnt one of these bridges when you came to this island. You burnt another bridge when you went out of this island. Now this bridge here. First of all, you cannot leave this bridge because you have to burn all the bridges. So definitely you'll have to come back here. And when you come back here, you burn this bridge and you come to this island again. Again, you are trapped. You do not have any to go. For all these islands we are going, they should always have them. So I need one bridge to come to the island and one bridge to leave the island. Oh my! I am using one bridge to get this home island. So when I go out of this home island, I have burned this bridge. And now at the end, when I have done everything, I have to return back to this home island. Bridge to come back. So it cannot have, again, your home island, it cannot have a degree 1, because when I use that bridge, I burned it. I need one more bridge to come back. And again, same. Can it be 3? So 1, I used it to go out. Second, I used it to come back in. If there was third bridge, I'll have definitely to burn it. So I'll burn it and go out. And again, I have to come back. So I need one more. So this one also is operating into pairs. If you look at any island, it should always have an even number of bridges on it. If it doesn't have, you will get trapped into your bucket and you'll not be able to come back to the place where you started from. So here we prove that if there can be no vertex with odd degree, if there exists a vertex with odd degree, you will be trapped and the graph will not be Eulerian. So we proved it in one direction. Is it true in the opposite direction? So note that these two statements are different. So the first statement is if a graph is Eulerian, then all the vertices in the graph have even degree. There cannot even be a single vertex which has an odd degree. What about this? If I say that if all the vertices in a graph has even degree, then I can guarantee you that this graph is Eulerian. Is that true? It's saying that you look at a million node network, and if all the nodes in this graph is even degree, you can actually declare that there will definitely be an Eulerian trail in this network. And note that the previous statement and this one are actually different. How do you prove this one? I have told you that all the islands have even number of bridges. Then what we are saying is we can actually burn all these bridges and come back to the home island. And how do you prove that? So to prove that, let's take an example. In the example, I am taking a network here. So how I'm taking that network, I'll just draw a figure here without lifting my pen, and I'll get a graph which is having an Eulerian trail. So I start from here and then I go here. I'm not going to lift my pen. That will result in an Eulerian trail, and the resultant graph will be Eulerian. So this is some complicated graph. Okay. So this is a graph which definitely has an Eulerian trail. And if you look at this graph, all the vertices have an even degree. You can actually count that. I'm going to number these vertices, label these vertices. What we'll try to do, we'll try to prove it by construction. So by construction means here I'm going to tell you if in a graph you have all the vertices with even degree, how do you actually go forward and find an Eulerian trail in this network. So we are going to prove that in any such graph, you can always end up finding an Eulerian trail. So we'll have an algorithm for that. And once you have an algorithm for that, it means that the graph is Eulerian. Okay. So again, let's say my home island is A, and my aim is again to walk through this city, burning all these bridges and return back to A. How can I do that? I start from A, I go to B. So I'm just trying to do this in some way. I start from A, I go to B. This edge A to B is burnt, right? Then let's say I start from B, I go to J, this edge is burnt, and then I go to from J to H, this edge is burnt, and then I go from H to A, this edge is burnt. I've done something wrong. I ended up in my home island, but the problem is I have not burnt all the bridges. We are going to make one observation from here, and the observation is I'm starting here from my home island, right? And then I go to some island from here, maybe a random walk, some other island from here, some other island from here. So when I keep going, so I'm randomly going from one node to another. What you should observe here is when you take this random walk and you end up at some place here, then this place can be nothing else other than your home or other than this node A. Why? So if this is the case, you start from some vertex, you go from go to some other vertex, go to some other vertex, go to some other vertex, and here is the place where your walk is ending. So when will your walk end? When this vertex over here, it has no more edges. So you cannot use any bridge basically to get out of this place, get away from this place. Then this place has definitely to be your home and nothing else. Why? And the reason is again because all the vertices have even degree. So every island you see here has an even number of bridges. So whenever, let's say, I started from my home and I came here to this island, so I used one bridge to come here, which I have burnt now. Then I know that since it had if this place has an even number of bridges, there should definitely be another bridge to go out of this. And if again during my walk sometime back I come back here, so this now becomes three bridges, I should have a fourth one to go away. So I cannot get trapped in any other island other than my home island if I'm taking this random walk. And that is what has exactly happened in this figure. So you see here, we started from A, went to B, went to J, went to H, and came back to A, right? And then I cannot get out of A. I am trapped. There are no more bridges, and this A is my home island. What if I did it something like this? I went from A to B, burnt this bridge. From B, let's say I went to K. From K, we go to F. From F, we go to L. You can actually do it and see that you'll never get trapped at any other place other than your home island. Even G, I won't get trapped. H, I won't get trapped. I came to I don't get trapped. I come to B, no trap. I come back to J, no, I'm not trapped. From J, I come to H, still I'm not trapped at H. And then I go back to A, and now I'm trapped. So, whatsoever kind of path you take from here, you'll always end up trapping in your home island. And that's what you want. So you should end up in your home island. But the one problem now we have is when you return back to your home island and you don't have any other bridge here to again go away from the home island, the problem is you might not have burnt all the bridges. So how do you do that? Assume that instead of a real life situation, it's a kind of a video game or something which you can simulate again and again and improve upon your solution. So just give me a moment. I'll go back here, uh, deleting all of this. So one thing for now, we are sure that the only problem we have is if I start from my home island, I'll end up in my home island. The problem is I might have missed certain bridges. So here, let's say this was my experiment number one, simulation one. I started from A to B. From B, I came to J. From J, I came to H. And from H, I came back to A. So I'm back at my home island. These four bridges have been burnt, but there are remaining bridges in this town which have not been burnt. So I can learn something from my solution now. I know that I'll again simulate it the second time, and this time I'll take a better solution. So what will be the better solution? What I have done is I started from A, I went to B, I came to J, came to H, and back to A. So what I know for sure is from some I have taken some wrong bridge across the way. I shouldn't have come back to A. Probably from B, I should have gone somewhere else, or from J, I should have gone somewhere else, or from H, I should have gone somewhere else rather than returning to A. So, how do I improve upon my solution? I can actually improve it by taking some other path from any of these nodes if it exists. So, is it so possible that none of these nodes have any other path? That is not possible. Why? Because this is a connected graph. So I have here A, B, J, H, A. And what we are saying is definitely there is some other path I can take from B, J, H, or A. If there was no other path, it means that this remaining graph is disconnected from this graph which we have explored till now. But this graph is connected, so there should be some edge which is connecting these two components. So I'm going to take that edge. So what we are going to do here is, so A, B, J, H we have already explored. So what we are going to do, you can assume that this portion of the graph has been deleted. What I'll do now, from B, instead of going to J, I'll try to take another path. So I know that this path, these bridges I can burn. So I start from A, I come back to B. From B, I'll do, from B, I'll take some other path such that I come back to B, and then I again burn this bridge BJ, JH, and HA. So from this B, I'm going to take some other path. Using that path, I'll try coming back to B and then take this remaining path so that I burn some extra bridges. So what we are going to do now is from A, I come back to B. Now the question is from B, is it possible that I burn certain bridges and end back at B? And that is again possible. Why? Because for now we know that the bridges which we have burned, they have an even degree. So for A, we have explored, we have burnt 2 bridges from A, 2 from B, 2 from J, and 2 from H. So even still now, every vertex or every island in this town has an even degree. So what I'll do now, from B, instead of going to J, I'll set out on another path. From B, I'll go to C, and from C, I'll go to D. And using the same principles we will use for, even now, there will always bridges to come into an island and go away from an island, because each of these has an even degree. Come to E, from E come to F, and let's say from F I come back to B. And there will always be path to come back for the same principle which we used earlier, because even B has an even degree. So we should be able to return to B. After returning to B again, then we can go back to the same path J, H and A. And again the problem is, yes, we have burnt many bridges and we have come back to A, but again not all the bridges have been burnt, right? So again what we can do is, we know that we can burn these many bridges. So again we know that instead of, so when I was going along this path, at some place I should use some other edge. So this time what I'll do, so currently, so initially my path was A, B, J, H and back to where I was left out with certain bridges. Now I modified this path. I said it is A, B, J, H, A, but from this B, I'm going to take another direction, and that direction is going to be from B, I'll actually go like this: B, C, D, E, F, and then back to B, right? So my path become A, B, C, D, E, F, B, and then J, H, A. And again, some bridges are left out. Using the same principle, what I'll do now, from F, I can again go on a different path. So from F here, instead of directly going to B, I can actually take this path, go to L, and from L you go to J, from J you go to G, from G you go to H. What I'm going to do now is, from this F, I have actually changed it. You go to L and then J and then G and then H. So in the same way, you can keep modifying this path to take into consideration more and more bridges. So what we are doing is, we are starting with a smaller solution, with a small solution, and over a period of time, we are going to add more and more edges to it. And at the end, you can actually end up exhausting this entire graph.